Okay, let's continue with block 2. Block 2 is concerned with the compilation of a specification into hardware or software. Let's first discuss the differences between interpretation and compilation. The difference is twofold. One thing is that the interpreter is extremely versatile. It does not know what kind of specification it gets as an input, so it needs to cope with every single possible specification. Thus, the code is pretty much convoluted and hard to verify or argue in any way why it is correct. The second difference is that the interpreter, when it is compiled into executable code, doesn't know what kind of input it will get, so it cannot possibly be optimized for a certain specification. And both of these things are extremely detrimental when designing a CPS, so it makes sense to opt for a compilation instead. So in the compilation, we take a specification and compile it into some high-level code. In the case of our hardware compilation, this high-level code is VHDL code, where VHDL is some hardware description language. And this VHDL code will then be compiled down to something executable. In our case, this is a synthesis procedure where we realize the code onto an FPGA. Now, for the compilation from specification to VHDL code, there are three challenges that we want to tackle. First, we want to keep the circuit cost as low as possible by reusing logic whenever possible. Second, we want to utilize parallel execution to further improve the performance of the monitor. This is particularly interesting for hardware because here parallelization is pretty much for free, if possible. And lastly, we need to take care of the split between periodic streams and event-based streams. So let's see how we do this. The general overview looks like this. We have our system, and the system produces values that are then sent to the high-level controller here, which takes this data, sends it to the queue, and the queue then relays this information to the low-level controller, which takes care of the evaluation. And after evaluating the event or the deadline, we send the information outwards back to the system to do whatever with the information. So let's have a look at the internals of the monitor here. The HLC consists of pretty much three components. We have the reception component, which takes care of accepting events from the outside, so from the system, and it has an internal clock which takes care of deciding when we have to evaluate periodic streams. And the information from both of these components is sent to the queue connector, and the queue connector unifies this information in such a way that what gets out of the queue connector is generic enough such that the LLC does not need to know whether the information it gets represents a deadline that is due or an event that is that has arrived at the monitor. So this way, we first of all take care of the split between periodic and event-based, and we reduce the circuit size of the LLC because it's agnostic towards periodic or event-based computations. And then the LLC is built in such a way that the evaluation utilizes parallel execution whenever possible. So let's first have a look at the HLC in detail. What you can see here is that the queue connector has two outputs towards the queue. The first one is a single bit output, which just indicates that we want to push an event on the queue. And the second one is the data we push on the queue. And this data consists of these many bits. And here, SI shows how large a single value of the type of an input stream is. So this way we can send a full event over the data link to the queue. The additional bit here indicates whether the value before that is actually valid, so whether we get a new value for this event, for this input or not. And these bits here are reserved to send a timestamp from the HLC to the LLC. And lastly, here we have n bits, where n is the number of output streams we have in the specification. And this is a unary encoding showing which output streams are affected by either by the deadline or by the event that we received. So to understand this encoding in detail, let's have a running example here. And this is a mild variation of a specification I showed you before. Here we again have two input streams, velocity 1, velocity 2. We compute a deviation of them, and we compute whether this is a lasting deviation by checking 3 consecutive readings, values of the deviation stream, and decide whether they all exceed a certain threshold. We have a trigger if this is the case, and we have an output that checks computes the average deviation with a sliding window over 10 minutes, and the trigger checks whether this value exceeds another threshold. Now, if we get a new event, and this event only covers velocity 2, so we get a new value for this stream only, then we can see that the first 64 plus 1 bits are 0. The first 64 bits indicate that there's no value, or this could be pretty much anything. And the last bit is a 0, which indicates that there is no update for velocity 1. Then the next bits are the value for velocity 2, 64 bits, and 1 bit indicating that this value actually makes sense and is a new update. Then we have a timestamp, the timestamp when we receive the event, and we have 5 zeros. And this shows that none of the output streams is supposed to be evaluated, because deviation has a pacing that needs both velocity 1 and velocity 2 at the same time, which is not the case for this event. Then we have the lasting deviation stream, which depends on deviation. And since this was not extended, lasting deviation is also not extended, and the trigger depends on lasting deviation. Lastly, the average deviation here is a time stream, so it's unaffected by the event anyway. So this is why we get 5 zeros back here. Now suppose that the next event covers both velocity 1 and velocity 2. Then we send both events here, both with a 1 at the end, indicating that this is an actual update for the input. And we send the timestamp. The affected streams are then the first 3 output streams, because they all depend on deviation, and deviation can be computed since we get an update for both velocity streams. Lastly, assume we are at time point 100 seconds. In this case, we have to compute the average deviation here because the frequency is 10 millihertz. So in this case, we do not get an update for any of the input streams. We send a timestamp, which is 100 seconds, and we indicate that the last 2 streams have to be evaluated. And what happens here is that by doing this, we already fulfill 2 of our challenges. First, the LSC can be agnostic to periodic or event-based streams. So we reduce the circuit cost, and we have taken care of this split. So these 2 challenges are taken care of. Now, let's have a look at the LLC. Here we can see that the LLC consists of 2 different state machines. The first state machine here just takes care of communicating with the queue. So it's the simple 3-state machine where we are idle, then we pop something from the queue, and we evaluate. And while we are in this evaluate state, the other state machine traverses itself once, starting in the idle state, then going through different evaluation modes and returning to the idle. And at this point in time, the other state machine also goes back to idle. Now the question is, why do we have different stages of evaluation here? And the answer has to do with the parallel computation. So let's have a look at the dependency graph of the specification. Here we can see that the deviation stream depends on velocity 1 and velocity 2, and both the average deviation and the lasting deviation depend on deviation. However, they do not depend on each other. So it doesn't matter in which order we evaluate these 2 streams. In particular, we can also evaluate them in parallel. And this parallel execution comes for free in a hardware setting. So that's something we want to do. And you can see that each of these levels here, each of these layers, represent a part of the specification that can be computed in parallel. And this is what's represented by these different stages of the evaluation here. So in the first stage here, we update all input streams. In the next one, we update everything that is in the certain layer of the dependency graph, in this case, just deviation. And then next layer, we have the lasting deviation stream and average deviation, which we can compute in parallel. And in the very last stage, we compute both triggers at the same time. So this way we can utilize hardware parallelization quite well. Okay, and for our running example, this then looks like this. We have these different stages, and the trigger stage here, those 2 triggers are then connected to the system and provide feedback if necessary. Okay. Okay, now we have the compilation. We have understood the compilation. Now we wanted to evaluate empirically what happens here. And this is the results. So we had two major specifications. One was a large drone example where we once again cross-validated a couple of sensors. And we had a network example where we checked whether some spurious network connections took place. And what we found is that the memory consumption was really low, as expected. Here in this case, we needed 3,000 flip-flops, and each flip-flop is a 1-bit memory cell. And for the network, we needed less than 2,000 memory cells. And the power consumption, this is the peak power consumption, was around 1.6 watts, which is extremely low and usually doesn't pose any problem on the system at hand. The evaluation time per event was around 4.2 microseconds. And here you have to be careful. You cannot compare this against the time we needed for the interpretation, because the interpretation ran on a high-end computer, whereas the evaluation here took place on a relatively easy and inexpensive FPGA. So the clock frequency of the FPGA was low to begin with, thus the evaluation time was also relatively high. However, we wanted to see what kind of an impact the parallelization had. So we came up with a command response property. And the idea here is that we have some common principle, some common data, and we want to check several properties that are independent of each other, but depend on this common piece of data. And while this seems like a synthetical example, we will see in the integration part that something like this is actually highly relevant in practice. Here we once again measured the evaluation time, and we can see that the time in microseconds for the parallel execution was 3.77. And by turning off the parallel execution, it went up to 43.83 microseconds per event. So there's a drastic difference here. Okay, to summarize, this is the hardware compilation. So we compiled the specification into 3 parts: a high-level controller taking care of the timing behavior, a queue as a connector between the HLC and the LLC, and an LLC consisting of 2 state machines that utilizes parallel execution of the hardware. And now you again have a chance to ask questions.